Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Talk will be, here I titled it, Properties of Large-Scale Communication Networks. In general, it doesn't need to be only communication, but many of the things here apply to, in particular, the internet. So this is kind of a normal application of it. And this work was actually done when I was in the physics department at Bar-Ilan University with my supervisor, Shlomo Havlin, and with several collaborators at Bar-Ilan University, as well as some people at Hebrew University, Clarkson, Tel Aviv, Boston. Let me outline the talk for a little. I will start to speak a little about history of random graph theory and how well does it apply to real-world networks. And then I'll speak about the tomography, which is the structure of layers, that is the quantity and properties of vertices that are at a certain distance from a given vertex. And then about the average distance of scale-free networks. Then I'll speak about disorder, what happens when edges have weights, about stability and immunization, and if I have time, I'll reach more advanced percolation properties, that is critical exponents, and directed percolation, and embedding of scale-free networks in Euclidean space. Okay, so, well, to start historically, graph theory started at Königsberg with Leonhard Euler, who started by asking whether the 7 bridges of Königsberg can all be crossed without going twice through one of the bridges. And this question was open for a long time until Euler managed to solve it by actually turning the topological problem into a network. So this was, in a sense, the birth of both graph theory and topology in general. And actually, a few years later, another bridge was added, and then the stroke became possible. So this is kind of a bridge, especially for Euler. If you want that. What? No? Okay, so this was kind of the beginning of graph theory. And in physics, many people studied many networks, such as grids, triangular grids, and also more less structured networks like spin glasses and these sort of networks. But usually the networks that were studied were networks in real space, networks that were embedded in three-dimensional or two-dimensional spaces. This was what was studied until the 1960s. However, if we look at large-scale networks, such as the Internet, World Wide Web, power lines, biological networks, and the sorts, they have several distinctive properties which make them not amenable to such treatment as just given graphs. That is, they are very large. They are dynamic, so they change over time. So it does not make a lot of sense to speak about the structure of the Internet because this will not be true a week from now. And they're only partially known. There are partial maps of the Internet. There are robots going over the World Wide Web, but they don't have all the nodes and etc. For most of these networks, this is true for biological, of course. Not all edges are known, and the edges that are known, biological networks are mainly network of interaction between genes, between proteins, between genes and proteins, and the edges are known. Each edge takes, I think, a few years in the lab to establish it. So the first attempt to look at networks by not studying the properties of a single graph, but looking at ensemble of graph was of the Erdős and Rényi model, started actually in 1959, the first paper. And the main idea was that it was democratic and random. You just take a dice and you throw it, and this is how you establish for each of the possible edges, the n squared over 2 possible edges, you establish whether it will be populated or not. This was the idea of Erdős and Rényi. And what they got, actually I think Bolbas proved it, but what they got was the Poisson distribution for the number of edges emanating from each point, from each vertex, and several other properties which I will discuss later. So here are the properties. The ensemble they speak, actually there were 2 possible ensembles. One is the ensemble of graphs with n vertices and m edges. The other is the ensemble of graphs with n vertices and each edge is populated with probability p. However, these ensembles are very much alike, and it was proven that for at least most of them, you have these properties. And the degree distribution is Poisson, as I mentioned. And what was maybe the most known result was the phase transition. Really, this is a giant component in terms of the mathematician you like to use. Spanning clusters, more physics use. And for larger than 1, there is a spanning cluster which has order n vertices. For exactly 1, the largest cluster is of order n to 2/3, which is what was then known as the double jump. The size of the spanning cluster, when it exists, has also been established, and as well as the behavior near the critical point, which was linear, and the average distance, which is logarithmic in the number of vertices. Now, the internet is one of the most studied and largest networks that exist, and it is a physical network, which means that the edges are well defined and are physical, actually, usually. And this is a map of the amount of internet transportation between countries. This is the map of the internet itself, not a geographical map, but just well, it just maps the topological structure of the internet anyway. And well, I'm not sure, but probably something like AT&T and MCI or whatever, yeah, Sprint, I don't know. But anyway, this is, I think this is from Lucent. And the internet has been mapped, and it has been established that if you take the number of nodes having a given degree, as you can see, this is a log-log plot. So the number of nodes having a given degree decreases algebraically. It is not Poisson. This means that the distribution has a much larger tail. In a Poisson network, there is no chance of having vertices with over 1,000 links, as in here. So what has been shown afterwards for many other networks is that the exponential network obtained by the Erdős-Rényi process is not the kind of network that we get in nature. The kind of network that are obtained in nature are scale-free. That is, there are several nodes which have a very high degree, while most nodes have a low degree. And the entire range in between also exists. So the distribution is a power law, or at least approximately a power law, whereas in Erdős-Rényi it's Poissonian. Here you can see another example, which is if you take the road map, the distribution is very close to Poisson. Every city can have no more than just maybe a dozen roads emanating from it. While if you take this is a map of Northeastern airline, and as you can see, there are a few airports which have a huge number of flights going out to them, and while there are most other airports just have one or two, a few flights to close by destinations. So the distribution here is much wider and approximately a power law distribution. Other examples are trust networks, which is the network of RSA codes used for electronic signatures, email networks, which are the network of how many or who are your the people who are listed in your address book, electronic address book, and the World Wide Web. The World Wide Web, actually, both these networks are directed. The World Wide Web has been mapped pretty well, and both the in and the out degree have a power law tail. As long as you can see, it can reach a few thousand links, and both the in and the degree naturally, since a page can not have an infinite number of outgoing links, though there are lists with many, many links. So, Erdős theory is not appropriate to describe real-world networks. There are actually a few places where it does not agree. The first one is the degree distribution, which is Poisson in Erdős theory, while it is a power law in most real-world networks that were studied. The distance in Erdős-Rényi networks is logarithmic, while in real-world networks it is almost constant. For instance, yeah, well, I did not mention this to begin with, which probably I should have. But what we're talking about here is mainly networks that are sparse. So in the internet, for instance, we assume at least that the number of edges is proportional to the number of sites. It is not. It does not grow faster because of economic reasons. And it seems all networks that were mentioned earlier are sparse. They all have a power law with the power law exponent. If I go back to it, the power law exponent lambda determines the behavior. And when lambda is larger than 2, which was established for almost all known networks, then the network is sparse. The number of edges is order n, and therefore let's say the fair comparison should be to sparse Erdős networks where the distance is logarithmic. And third property is stability in immunization. So if we look at Erdős networks and we want to calculate the critical concentration for percolation, that is, what fraction of the nodes or of the edges should be removed before the network collapses and loses its giant component, this is the formula, and it is about 30 to 50% for the measured average degrees. While if you look at the threshold for infectious diseases, for instance, in the population, you get about 80 to 90%, 99% critical concentration for immunization before the network is completely immunized against diseases. In the internet, again, if you look at virus spreading, you get about 99% immunization rate if you want to completely stop viruses from spreading. What, smallpox? Why? Because it's slower? Well, I'm not sure if this is the reason, but maybe you're right. I don't know. The numbers are taken from Anderson and May. I'm not sure if there are no other diseases that are lower and weren't mentioned there, but these are the numbers they gave. So maybe they're even based on experiment, at least partial. The black peg, I don't. Okay. So here's another example of experimental data. This is the average time of life for computer viruses. For here, there are boot, file, and macro viruses. I guess everybody here knows what are what, and what's the meaning of all those viruses kind. But anyway, it doesn't matter so much. What is important is that you can notice that the lifetime for viruses is extremely long. It's about 14 months for boot and macro viruses, and 7 months for file viruses. And some viruses can live up to about 3 years, although the average time for infection may be minutes or days. So this is actually a huge number, and this was very difficult to explain. And that's well, they exist in at least statistically significant numbers, and anyway, by normal epidemiologic theory, there should be some threshold for viruses. So either they manage to very quickly infect the entire network or almost the entire network, or they are very quickly abolished at all. And here you have very long propagation time, though if you look at viruses, usually the main infection is within a few days. You can get up to several years that the virus still propagates in the network and keeps infecting people. Yes, this is exponential decay for the time. Yeah. So the first model that was proposed for how come networks are different than the regular Erdős theory was by Balabashi and Albert, and it has two main properties. First one is growth. Real networks grow. So the internet, for instance, is constantly growing and has new routers and new end units connected to it every day. The World Wide Web, the same, also is growing. And in biological networks, well, usually you can say they grow through evolution. So most natural networks keep growing. And the second key ingredient was preferential attachment. This is the notion that instead of connecting each new site to the network randomly, they are connected degree of the sites. So there is a higher probability to connect to existing high degree sites than to low degree sites. So here's an example, a site, and two other sites which in this case have rather high degrees in this network. This was in paper and later solved more rigorously in several other works. And it has been shown that the degree distribution is power law with power exactly 3. Later, there were several variants of this model that included nonlinear preferential attachment and addition of a constant term here, and all sorts of other changes. And then you can change the exponent and add an exponential cutoff and all sorts of games around these basic notions. But usually most existing theories for the formation of scale-free networks are based on more or less these two ideas. So the second thing I'd like to look at is the tomography of scale-free networks. Although many of this applies also to any generalized scale-free network. So the main idea is to start with the highest degree node, which gives the simplest equation, since its degree is rather well known and the fluctuations around it are rather small compared to its size. So we start with the highest degree node as the center of the network, and then you count the nodes at each layer around it. So the degree of, so what we're looking at is two things: the degree distribution nodes around the central node, and the number of nodes, or the mass, in each layer. So here you can see simulation data for the degree of each of the nodes at each one of the consecutive layers. And what you can see is that this behaves like a power law with an exponential cutoff that is changing with each layer, is going lower and lower. So here is the theory. You can take the degree distribution, which is just this, normalization factor, which is missing here. And this is if no outside constraints are imposed, this is the degree of the highest degree node. By just taking the degree distribution and checking what is the degree, the probability of having the highest degree among, and this is just extreme value statistics. Okay, so this is the degree distribution when you are considering all the nodes outside a given layer. So what you do is just give recursive equations. We have here layer number L, and we add the nodes that were still unconnected with random matching. So random matching can have both links going from one site in the elf layer to another site, or from one site in the elf layer to a site outside the elf layer. Okay. So you can write. This is the configuration model, the standard configuration. We haven't done it on Barbashi-Albert networks, though I think we have compared numerically to simulation of Barbashi-Albert, and it's very similar in the distribution of layers, but it probably might be even easier to solve it for Barbashi-Albert, since the network is completely connected, while here it is not. The giant component is not 100% of the network. Okay, so you just can write. I won't give the details since I have no time, but you can write recursive equations for the highest degree of the nodes outside a given layer, and for the number of sites, number of nodes at each layer, and these can be solved numerically. And what is is the layers in comparison with the real internet data. So this is the data of Lucent routers, and the other line, the red line, is the results of the recursive equations. So you can see there is a rather good agreement with real internet data, even in this simplistic configuration model. So at least to explain the layer structure of the internet, there is no need to include either clustering, more connections between. This is in a semi-log plot. The deviation here is actually a result of the mean field equations. The mean field equations tend to overestimate the tail. And now, if you look analytically, there is some sort of an average distance, and we want to look how it depends on n. So again, you can do this exactly in the limit of large. You can do it exactly for in the limit of large n, and what is obtained is for lambda larger than 3, the distance is the network. For lambda between 2 and 3, it is log n, which we termed ultra small. And for lambda, this is n over log n, this result. So the real world looks like a constant. So there are two possibilities. One, well, what we also show is that for scale-free network is a little over 2. Well, it depends what exactly is defined. You can take it at the autonomous system level or at the router level. It's somewhere between 2.1 and 2.5, depending how exactly you take it. But yes, of course, there's the equal sign here is not appropriate. This should be a constant here, of course. And the constant depends. Yeah, the constant depends on the over log of lambda minus 1, if I'm not mistaken, or something like that. It's this over the log. Yeah, exactly. Lambda 2. So this is.
That was my question. It's here
that.
Which has lambda n.
Yeah. This we give also the constant here. This is, of course, not exactly mathematically rigorous, but there is later work of Chang and Lu who do it for a very similar model, though a little different, but they also get the same result. And I'm not sure if the limit of lambda goes to 2. I'll look there. But okay. Anyway, what we do show is that actually for any lambda larger than 2, you cannot have a constant diameter or constant average distance. You can construct the smallest diameter possible network for any scale-free distribution, any power law distribution, and for any lambda you can get log n, even lambda larger than 3, if this is not a random but a specially constructed network. But it can't be lower than log n. Yeah, well, if lambda is 2, we're talking about the limit here, so actually it's not sparse. So this is not a sparse network. I just give this result here because it's the limit of this. But actually, you're right. It's not sparse. If you take a cutoff, then depending on the cutoff, if you take a constant cutoff, of course, it cannot be constant. If the cutoff now depends on n, then I guess it depends on how it should, how it exactly depends on n. I think there are some results of Dorgovtsev and Mendez. I think they speak about what is the lowest cutoff you can take in order to still obtain this behavior. Yeah, you don't get the sparse matrix, right? You get a... Oh, you divide it by the log n, and you say it goes back to a constant. Yeah, you're probably right. Yeah. Well, we didn't look at it as so much as a limiting case, but as a separate case. So you can just calculate for lambda equals 2. If you take the natural cutoff, which is what we did, you just get the natural cutoff is n. There is a site with degree. So the average degree is log n, exactly. And you have a site which is already connected to a fraction of the sites. So this is kind of easier to do. Now, what I wanted to speak about also was the case where there are edge weights on the graph. So suppose there are edge weights, and we are looking now at the distance, which is now the sum of the weights across a path. What happens? Well, so here is an example going, for instance, from A to B. The shortest path is not the optimal path. The optimal path goes through here. Usually, Gene gives this lecture, and he has a nice story about being stuck in traffic in Boston. Since I've never been to Boston, I'm probably not a good witness of this story, so I'll just give the facts, which are... Well, we want to look at the minimal, that is the minimal energy, that is the optimal path between any 2 points. And we can think of 2 possible ways to put the edge weights. One is what we call weak disorder, in which the distribution is narrow, for instance, a uniform distribution. And for the sum of all the terms along the way. While strong disorder is choosing a much wider degree, a much wider weight distribution. So, for instance, a distribution in which every weight is twice as large as the next one. Then the product of the entire path is called a single edge along this path. So, for instance, for example, broadcasting video over the internet is an example of strong disorder, since the narrowest link along the way determines the entire capacity of the path. So here are the results. The results are obtained, well, I'm not sure I'll even get to it, but the results are obtained from getting a mapping of this problem to the problem of percolation on the network. Yeah, this is kind of the first passage, though I... Yeah, there... Yeah, well, I've seen work on first passage, especially by Van Hofstad and I don't know about some people, but I think they never took a look at the strong disorder limit, which is kind of very different from the weak disorder. So in weak disorder, what is known is that whenever the weights are more or less uniformly distributed, then the optimal path tends to be very short to the shortest, very close to the shortest path. you don't get too large deviations, since it's not worthwhile to seek one path. However, if you take optimal paths, as you can see here, the distances become much larger. The distances become n to 1/3, or in the case of scale-free networks, n to some power, which is very different from the logarithmic distance of the shortest path. Okay, so you can do it two ways. One way is just to say that the weight of paths. Well, you can say this way. You can just take a path. This is not working. You can take a path and write the weights here. And now order them decreasing order. So this is, say, W3, W1, W2, and W4. Then you lexicographically compare it to another path. So the highest weight determines, and if it's exactly equal, then exactly equal can only happen if they go both through the same edge. So, okay, so the weights are random. They can represent, for instance, the bandwidth of a given communication line. They can represent the cost of transmitting through this line. They can. Okay, so if you want to use this method, then you can do it on any arbitrary distribution. At least as long as the distribution does not give exactly the same weight, it is, let's say, continuous. If you want to take the sum, then this approaches this case only when the distribution is very wide. So a distribution which is very wide, in which every weight, for instance, is twice as big as the next highest weight in the network, is going to give you the same behavior. Okay. Yeah. Yeah.
Let's say the mode is that you think of having bandwidth, and the narrow aspect is
Yeah, exactly. But
take the min of the bandwidth.
yeah, but this is where the analogy a little breaks down, because if two paths go through the same edge, then and this is the narrowest path, you compare the next narrow one between them to determine which has the lowest. And this is not exactly what you do for the internet. You don't care so much, unless you say this path may get jammed or something, then it will be the norm. So I'm not looking at the weight, but at the length of the optimal path, number of edges on the optimal path. The edge on the optimal path is much larger than the logarithmic distance. So this is analogous to what is known in finite dimensional systems. That in finite dimensional systems in weak disorder, if you take the shortest path between points, then it is known that on weak disorder the optimal path will tend to be self-affine. So it will still be of length approximately L with some smaller order corrections, while the optimal path can be much larger, and it's actually fractal and has a higher dimension. Yeah, well, I don't know about rigorous proof in the strong disorder case, but in the finite dimensional. Yeah, well, yeah, usually those problems tend to get easier when speaking of networks than in finite dimension. So this is, yeah, well, the analogy is, okay, I don't have it here, but the analogy we use is kind of the same as what you say, is starting adding, yeah, start adding randomly at a random order, or if there are really weights, you can add it in the order of the weights, but this order is random if they are independent. So you add random edges, and whenever an edge closes a loop, you just remove it again. So you get a. So this actually applies also to the minimum spanning tree, which has exactly the same construction. So this is not only the distance of the optimal paths, but also the diameter, or at least the average distance, on the minimum spanning tree on a random network. And in this is exactly the algorithm, so you don't need any assumption on the weights, except maybe that they are continuous. So I talked to him a little. He doesn't know of any work done on random minimum spanning tree on a random graph, or even the complete graph. But well, Bolobash also told us once that he doesn't know of anyone who has actually proven this. So this is kind of an still open question, at least in the rigorous sense. This actually is obtained also if you start from the complete graph, because it doesn't matter in which point you start. Okay, so how much time I have? Okay. So let me speak on the third issue, which is percolation. So I don't know if I have to introduce percolation theory here. Anyway, the main idea is just removing, or in the other case, inhibiting either sites or bonds. In this case, this is a site percolation. You remove the sites, and for each site you remove all of its bonds. And there is some transition point. This is, for instance, for the square grid. There is a transition point in which there is no more spanning cluster. This is what's called a spanning cluster, since it goes from side to side. And it is of size comparable to the entire network of other n sites. Well, here it goes both from right to left and from top to bottom, but I think there is a proof that both things happen at the same time, as far as I know, for finite dimensional. For infinite dimensional, actually, we couldn't find, I'm not sure if there is, but we couldn't find any nice definition like this for but I'm not sure if there exists a proof definition. Okay, so here you can see a giant cluster just broke down, and all you get is small islands. So this is what this phase transition looks like. In finite dimension, there is some critical point at which the entire thing breaks down. And from then on, the size of the cluster is comparable to the entire network. So here's an example again of percolation, just diluting the sites. Each color is a different cluster, and here you can see I've gone below the percolation threshold, and there's no more current from up to down. Okay, so let's look at stability of scale-free networks for instance, for networks which have degree distribution, which is a power law. So the question is, which was raised first by Barbashi and Albert, what happens if you take this network and percolate on it? You randomly break a certain fraction of the nodes. And the question is, where does a phase transition occur? And another question is, what happens if instead you can think of some malicious hacker going to attack the most important sites in the network, the most important routers, trying to break them down? What happens then? Is this different from random breakdown? And okay, what we show is for these two models, not only the critical threshold, but also the critical exponents are different. So the universality class depends on the way that criticality is reached. I'll speak a little about, if I have the time, about both of them. So here, intention attack. As you can see, in random breakdown for lambda larger than 3, you get phase transition. In this case, about C equal 1/2. While for lambda equals 2.5, the larger the network size, the more and more late the phase transition occurs. And for intentional attack, you can see that for different network sizes, the phase transitions actually occur at very low thresholds. About 6% of the nodes break down and the network collapses. This is the size of the giant component at each one. So this is for 3 lambdas, which you can see here. And this is just PC as a function of lambda for different lambdas between 2 and 4. If you take, well, I didn't speak about M, but M is the cutoff on the lower cutoff on the degree. So the lower cutoff in the degree, if you take it to be 1, then with lambda equal 4, the network is not connected to begin with. So we just get PC equal 0. But if you take a larger M, then it changes to, for M larger than 2, this changes to infinity. Well, as far as I know, Bolobash showed that for random attacks on Barbashi-Albert node networks, which is exactly lambda equals 3, he showed that the threshold also vanishes, so you must remove 100%. And for intentional attack, it's actually impossible for the threshold to vanish. If you remove a finite fraction of the networks, you already get a finite cutoff on the distribution. So this must have a finite percolation threshold. Okay, so if I look at the degree distribution, just okay, I'll look at the log graph, for instance. So this is P of k, and this is k. So if you take a look at the degree distribution, there is, for finite n, there is a natural cutoff that occurs here. But anyway, let's ignore it and even say that the cutoff is infinite. Suppose, but the average degree is finite. So if the average degree is finite, if I take a cutoff here, for instance, at k equals, I don't know, 7, let's say, then the entire weight of the tail is finite. The entire mass here is just a finite fraction of the network. Let's say, I don't know, 20% of the network. So I removed 20% of the nodes using intentional attack. I removed all of these. So what you get is just a network, even if you disregard the effect on the degrees of the remaining sites, what you get is just a network with the highest degree node is 7. So naturally, this network must have a finite percolation threshold. Since you don't get any long tail anymore. After only... Yeah, so it's a constant fraction of the network. So
I first remove the 10% of the node, then I get a final number.
yeah.
Then I do another 10% randomly, and then
Yeah, even you can look at it this way. You can actually calculate exactly using just the tail, and you can calculate the effect that removing the tail has on the degrees of the remaining nodes. Since you can calculate what's the probability of having an edge from here going here, if you know the weight of each of these each one of those sides. But anyway, I say even let's say you remove 20%, you already got a normal network, not a scale-free one, and then this must have a finite threshold. So there is a fundamental difference between intentional and random removal of nodes. And for this reason exactly, that after removing a finite fraction, you just make the network normal, then all the they are different. So, well, I'll just run the theory part. You can just do some consideration of branching process to sort of a tree expansion, let's say around the cluster, and do some math and get that the critical point is obtained when the ratio of the first two moments of the degree distribution is 2. So if this ratio is above 2, there will be a spanning cluster, while if this ratio is below 2, there will be no spanning cluster. This result was actually obtained before by Molloy and Reed in 1995. Now, if you... Okay, so you can use this criterion also for regular Poisson graphs, where you get back to the normal condition, and also for a Cayley tree. Now, if you do random removal sites, you can see the probability distribution changes, and what you obtain finally is this, that the critical threshold is 1 over kappa minus 1, where kappa is the ratio of the first two moments calculated on the original distribution. So what matters to calculate the percolation threshold is only the two first moments of the degree distribution of the network. Now, for scale-free networks, this is an approximation of kappa. And if you take the case of lambda less than 3, then the second moment diverges while the first converges. So what's obtained is that PC vanishes, the critical concentration vanishes, or PC equals 1. You have to remove 100% of the nodes to obtain the phase transition. Now, again, I'll skip the technical details of the generating function, formalism, and I'll just give you the results. So you can calculate the behavior near the phase transition. And what is obtained actually is that for lambda, even between 3 and 4, in the regime where there is a finite critical threshold for the phase transition, the critical exponents are different from the mean field exponents. You don't get linear behavior near the critical threshold. Instead, you get superlinear behavior and the smooth phase transition. When lambda approaches 3, the phase transition becomes actually infinitely smooth. It becomes infinite order phase transition. And here is also for tau, which is also non-universal. And also the fractal behavior. So you can calculate all the fractal dimensions of the percolated network and the analog of the Erdős double jump. And you obtain that all of these are not universal either. They are all different from what you obtain for Erdős theory. Okay, so if I'm looking at just the graph, then the chemical dimension, if I'm taking the number of hops, the chemical direction is kind of the dimension on the fractal itself. So it's the number, the mass, let's call it, of the graph. That is the number of sites within a distance, number of hops L from a certain site on the cluster. So that's the chemical. Now fractal is when you embed it into space, then you get also that each one of these paths behaves as a random walk. So you get 1/2 of this, 2 times this dimension. So if you look, for instance, at percolation at the 6th dimension, which is the upper critical dimension, then the critical dimension is 6 naturally. The fractal dimension is 4, but the chemical dimension, which is the dimension on the cluster itself, is 2. Okay, so this is kind of an open question. For lambda approaching 3, the dimension becomes infinite. Below 3, the behavior is still logarithmic even after the...
it looks weird because your fractal dimension is 0
Yeah, so so at criticality dimension is finite for lambda larger than 3, so I should have put this also here, but for lambda larger than 3, we know the behavior. Lambda 3 and below, we don't know anymore how it behaves. So numerical result that it's at least so there's no more power law fractal, but we don't have an exact proof for it or any consideration that can show it. But also, for less than 3, things become more complicated since the percolation method vanishes itself. But somehow with the n, and we don't know exactly how. So it's hard to find around it. So this is an open question. How it might be that you need completely different methods. I'm not sure. So this is the size, this is given also here. This is the size of just cluster and criticality, and this is the analog for scale-free networks. Now this continues. Okay, so you define this as a fractal dimension, then no, this is not a fractal dimension. Numbers here, different varieties of fractal behavior. Well, yeah. The same for any dimension above 6. And also for Erdős-Rényi, and also for fractal for a scale networks with lambda more than 4. Now this one doesn't seem to do anything nasty at lambda below 3, but we're not sure if it still holds or not. We don't really understand the critical behavior there. So, okay, move on. So one, maybe it's the last thing I'll talk about, but the critical threshold for scale-free network. Okay. So an interesting question, that's practical question that is asked many times is, well, we have shown that the percolation threshold is vanishing, and this means also that epidemics can propagate through the network regardless of how low the infection rate is. So this is a bad result, and also maybe even a worse result is, as we've shown before, that the threshold for random immunization in order to abolish a disease is almost 100%. So you must immunize the entire population to stop a disease. So how can you overcome this problem? So the usual suggestion is just to immunize or vaccinate those people that either are known to have many contacts or are known to have a high probability of getting these sort of things. However, finding out the degrees of nodes in the network can be a rather difficult task, either because it is not well defined and because it's hard to obtain information on this. So what we're suggesting is a method of doing this without knowing the degrees of the nodes in the network. And the idea is this. Take a certain fraction, say 30% of the population, randomly, completely randomly. Now, if you immunize those people, then it will not stop any disease, since this is way below the critical mass. However, ask for each one of these people to give you a name of a random contact of his, a random neighbor in the network, and immunize those neighbors. So although the neighbors are chosen randomly, the nodes with high degree tend to have a much higher probability of being immunized in this case, since each one of the neighbors may give their name. Yeah? Well, we would guess it can be applied in general. Well, there are some problems like, does the person really know who all his contacts is? Maybe there are, I don't know, people who go through the halls and you don't even notice them, but they can influence you. But I would guess it can be, at least in some cases, be applied. And I think targeted immunization, where they immunize people that are more likely to get the disease, is applied in many cases. But this method, I'm not know. Well, I should maybe mention here that after disease occurs, there is a method called contact tracing, which is basically to find all the people you have been in contact with if you got sick, and try to track down the sources and where the disease has spread, which is quite similar. So it works in very similar ways, though I don't know if anybody suggested of using this kind of technique for immunization beforehand. But they work more or less in the same way. So, well, I give just the results here. You can calculate this. And actually, you can do a more sophisticated case in which you only immunize someone if 2 neighbors recommended this person. And here, actually, well, there is also an exact solution of this by eigenvalue methods. I don't give it here, just the approximate one. But this can be solved. Both of these can be solved exactly. And here are some other results for other distributions, like 2 Gaussian kind of bimodal distribution and scale-free distributions. And as you can see, the immunization threshold goes from almost Okay, so do I have time or should I finish? Okay, so I don't have a lot more, so it's mostly automatic. So one thing I would like to mention is what happens in directed networks. So I won't go through the entire theory. There is a large work done on what is the structure of random directed networks, and this is an example, a real example from the World Wide Web, which has mapped about 200 million web pages. And there is a strongly connected component which contains the sites from which you can reach each other, and the giant strongly connected component. And there is an in component in which you can go out, but you can't go back in. And then giant out component which can be reached from here, but you cannot go back. These are many web pages that are indexed, for instance, but have no links outside. And those are pages that are not indexed, but have links going out. So we were looking also at percolation on directed networks, and I won't give the entire theory, but anyway, two important things is one, that there is the critical threshold is very dependent on the correlations between the in and out degree of the nodes. So each node has an in degree and an out degree, and the threshold depends on not only on the distributions but also on the correlation between them. And the second point is that there is a regime where the exponents, the critical exponents, are anomalous. And in this regime, there also, there can be different critical exponents for each one of these components. For the in, the out, and the strongly connected component, each one can have different critical exponents. And well, one last topic which I'll mention is what happens if you take a random scale-free network, but which is built on a grid. So the main idea is just take the sites on a grid, and for each one, randomly choose a degree according with some sort of, for instance, scale-free distribution, and then connect it to the nearest possible neighbors. And I won't go through the entire details since this is not so simple, but anyway, it can be done. And what is obtained, actually, this is only scaling arguments together with the results of simulations, but it seems to go rather well, is that the chemical dimension here is higher than the dimension of the embedding. So actually, in this case, you can go from point to point in the grid using less than square root of n, for instance, in a two-dimensional grid, using less than square root of n. There is some other power law, n to some power, which is smaller than 2, which is the average distance on this network between sites. So you get sort of a fractal anomalous behavior. So this is more or less what I wanted to say about this, so I'll just give the conclusions. So we've seen the tomography of scale-free networks and how the degrees of sites outside a given shell behave as the power law with an exponential cutoff. The distance in scale-free networks is very small, much smaller than even in random networks, and of course than in grids. However, if there is strong disorder, or you take, for instance, minimum spanning tree, the distances become much larger and are power law. Scale-free networks are resilient to random breakdown, but are sensitive to intentional attack of the mostly connected nodes. However, there is also another way to immunize without knowing the topology and the degrees, and this is using what we call immunization. Now, for the non-directed networks, both the critical exponents are different than in mean field percolation, so it's a different universality class. I've shown or gone through a method for embedding scale-free networks with where the distance does not with Euclidean distance between sites. And one last thing, which I didn't really mention, but for large networks, you can optimize the degree distribution to have maximum resilience to random breakdown or to attack or to both. So actually, if you have a certain number of nodes and a certain number of links, you can choose to put them in a smart way that will give you a much more robust network than if you just put them randomly. So, okay, this is what I had to say. Hope I didn't bore you too much. Okay, thank you.
So when you in and out, do you specify as a joint distribution?
So if you specify a joint distribution, which is not where the index is not independent of the yeah, you can do that. Yeah, they hook to some they have to comply to some constraint that the average in degree must